Good, thank you.
Yeah, I don't think this is correct.
All right, hi all. Just gonna do a quick like introduction and like 5-minute presentation on PHIT. Has anyone here heard of PHIT? No? Okay, great. So we have like a fresh new audience. So my name is Hannah Legaspi. I'm the Outreach Recruitment and Retention Analyst.
I'm Deeksha. I'm a data science major and one of the PHIT ambassadors for this year.
Yeah, so this is what public health informatics looks like in action. This is all just to show you how, health is becoming so digital now. There's a lot of inefficiencies and inequities with the current health infrastructure. And so if you're like interested in like breaking into like the healthcare field as a way to use, maybe like your AI skills or your technological skills, there's a lot of like room for that. Because there's all this data and, public health relies on data to solve questions and like problems. And so we need people who, understand public health informatics. And so PHIT is a workforce development program. We offer a minor and also a paid research and internship opportunity for you all, as well as also try to get folks who are historically underrepresented within this health workforce, because as we know, people from the communities are able to best serve these communities. So please join us in making public health more inclusive and data-driven. So here are just some highlights of the summer 2025 internship projects. So there was a lot of different types of projects that, students worked on and got paid for. And so one of them is a lab on campus where they, examined environmental health and environmental justice. They did analysis on extreme heat and wildfires. So all things very impactful and like pertinent to Southern California. And then we even had a student who worked with a startup health tech company, and they learned, GIS skills, and organize verified resources that is accessible now through a public health app. And you can even work with like a local community health organization. And, if that's something that's like close to your heart, you want to work on, you can do quantitative analysis with them, or you can do something like very health centric, like with a health quality center, and work on patient data, improving, like their outcomes and evaluating clinical measures. So it's a lot you can do. Public health is very broad, and there's a lot of skills to be learned and taken to public health. Oh, sorry, that's the old. We have a intern alumni panel. So these are all students who have done the internship and also are currently in the PHIT program. And so there's a mix of students here. Some are public health, and we even have one grad student. And so if you want to learn about their experience in the internship program and, just their experience in general, please feel free to join us on November 19th, COHS 3120. And we also posted this on our Instagram. And then now we're just going to let Deeksha introduce herself and kind of talk about her experience in the program.
Yeah, this will be very quick actually. I did my internship last winter with Dr. Wu in the E3 lab. It's an environmental equity lab, where I annotated solar panel images, satellite images, and then also edited and wrote machine learning programs to automate detecting those solar panels for climate change purposes. It was a 10-week internship program. Okay. It was very fun. It was very interesting to learn what, skills that I had not been taught previously in my classes. So I highly encourage you guys to, join us.
And here's some more resources. So I have office hours if you ever have a question or want to talk about PHIT, and the ambassadors have office hours too. You can have access to the more updated slides. I think I sent a link to Sri.
Yes.
And then yes, you can always email us at phitinfo@uci.edu. We are also on campus at ARB Suite 2030. That's our Instagram. We post all our updates on there. So please follow us. And that's a more general QR code for, more like anything that has our social media, our website, all of that. And so here's also a disclosure that we are federally funded. So if you keep up with the government at all, just please keep that in mind. But I do want to highlight the 7 million number that is awarded to all of us. We are in our last year of the grant. And so the last paid internship cycle that will be to exist for PHIT is in summer 2026. So if there's anything I want you all to leave with today is that there is a public health informatics workforce development program that provides internships, and summer 2026 is the last cycle you can get a guaranteed paid internship in the workforce. So yeah, we have all this money and we want to spend it all on you. That's how we pay for the internships. That's how we pay for y'all. So please consider joining us. And if you have any more questions, please feel free to hit us up there. Yeah. That's it. Thank you.
Thank you. All right, welcome in everybody. Today, we're gonna have a workshop. Aston, are you ready?
Yeah, should fit.
You want me to put screen up? Okay.
Should look here. Wait, can I airdrop you some stuff? Okay, thank you.
On this,
Yep.
this is my laptop, so keep about that.
Oh, shoot, okay, wait.
Do
Do you wanna put your,
It's because there's no charger.
Okay, so there's no.
You wanna use Vim's charger to charge your computer here? Where are the?
All right, let me just send it to you. Cause I need the visual version. Wow, there's quite a bit of people today. That's great. That's great. Very happy. Always good to see people around. Yeah, do you mind calling yourself first now? Thank you. I'm down. Well, I'll give you push it down. Thank you. We don't need the visualization now, but just get it. Yeah.
Okay,
Yeah.
where's the
Just need to be able to run 10 minutes.
slides?
We're not.
Does that
That's-
go?
yeah.
Okay.
Okay, yeah, so I'm freehanding this today, since it worked well last time, and so we'll see again how it goes this time. Yeah, I hope everyone's doing well. So, okay, in the last lecture, we sort of talked about, we continued our discussion about, finding the optimal parameters of a linear regression model. And so far, like, and sort of anybody remind me of like what we've done so far. Right, so please tell me you remember something from last week. I know you do, because we had a long discussion, and I do, and you do too, because we had a long discussion after, and I'd be very sad if we didn't get there. What did we do? Yeah, either one of you. Yeah.
We, if you take all of the, like features or, the name of it is not coming to my head right now.
Batch.
What?
Talking about batch.
Correct, yeah,
Yes,
batch,
yeah.
yeah, so we talked about batch gradient descent, stochastic gradient descent, and mini batch gradient descent. The idea of which we are in our parameter space, and we are trying to, in each parameter in our parameter space has a corresponding cost, which defines a cost surface over which we're trying to optimize. And we do so via batch gradient descent, stochastic gradient descent, or mini batch gradient descent, which calculates the gradient of this sort of cost function at a certain point, gives us the direction of fastest ascent in this cost surface, on which we are moving the negative direction. So we can, as we iteratively move along the gradient, we minimize the cost function. Does that sort of sound familiar to people who were here last time? Yeah, okay, great, good, very good, because I put a lot of effort into that. That's good. And we also, so I didn't really get to this, but like, there's also a faster way of a more direct method of evaluating the optimal parameters of a linear regression model, which is, well, directly solving for the gradient, right? If I have the cost function, if I have the MSD cost function, which we defined last time as oh, wow, terrible hand ratings. So I go over all my data points, right? And I find the difference between my prediction and my actual cost, or my actual output, square it, sum over it, and find the average, right? That's mean squared error. That's what we talked about, right? And well, we also know that, well, our prediction is actually just defined by our linear regression model, y equals theta 0 plus theta 1 x1 plus all the way to theta and xn. Everyone remember this? Good. Okay. So we can plug this. This is our prediction, and y hat generally represents our prediction for I data point. So we can plug this into here, right? And from there, right, that gives us our cost function for any given data point, right? I give you an X, I give you a Y data point, right, that I predict. I can tell you, right, like how well that prediction was, right? So that is that gives us the cost of a single training example. And from there, I'm not sure we should close the door because I'm being pretty loud as well because I need to project, but it's fine. From there, I can find the gradient, right? Which is just effectively taking the partial derivative of this function with respect to each one of these parameters, right? So like that's something we talked about last lecture as well, right? And that gives us the gradient. Well, what I'm saying is another way of doing this is besides like finding the gradient directly, right? And then iteratively moving, which is gradient descent. I can just solve for the gradient where the gradient is zero, because that's what we're trying to find, right? When we look at the entire point of gradient descent is to get to the point, get to the bottom of the curve, right? And the bottom of the curve is where, like in this one-dimensional case, the derivative is zero, right? But in our multi-dimensional cost surface case, right, we want to get to this gradient is the extension of the derivative, right? And so we want to get to the case where like the gradient is zero, right? So what we do instead is instead of finding the gradient and then moving in the direction along the gradient, right? I can just directly solve the case where the gradient is zero, right? And it turns out you can do this specifically for linear regression models, right? You can do this for specifically for linear regression models, and this gives you a direct way of solving for. I'm not going to go through the math here unless you really want me to, but you can directly solve for the optimal parameters theta that minimize your cost function, right? So it gets you to the bottom of the curve, right? Direct. You can solve it direct, as opposed to gradient descent, which is an iterative method of walking your way down to the bottom of the curve. Right? Yes.
What was the other one? What was the other gradient descent?
Batch gradient descent, mini batch, right?
What's the difference?
So the difference between gradient descent, mini batch gradient descent, and stochastic gradient descent is the number of data points you use per when calculating the gradient, right? So for example, I have a training data set, right? Which is just a bunch of which I might define as a bunch of x's, right? Which is the x vector, right? Actually, let me just write it out. So I have a bunch of x, y data points where each of the x's are vectors, right? And instead of using the entire data set, right, I use a part of the data set, right, to calculate the gradient. That's mini batch. If I'm using the entirety of this data set, I'm performing gradient descent, right? I'm calculating the true gradient. And if I'm only using a single data point, I'm performing stochastic gradients. I'm calculating an estimate of this true gradient via one data point.
Wait, so stochastic gradient descent is only on one point?
Yes, stochastic gradient descent is calculating the gradient on one training.
What's mini batch?
And mini batch is, well, as the name suggests, a mini batch.
Oh, just a small.
A small subset of them, right? And then batch gradient descent is use everything, right? And so, well, use everything, if you have a data set with 1 million data points, calculating this, or calculating the gradient, right? The partial derivative of this cost function with respect to each theta 0, theta 1, theta n, right? That's slowish. That's slow, right? That's slow. And then, my bad. And you gotta plug in, and you gotta do it and you have this sum over all of them and then divide by the entire data set, the million data points. And that gives you one iteration of movement.
And also, what is that downward triangle J data?
This is nabla. This symbol means nabla. This means find the gradient. Remember that, okay, so this cost function is a vector. Maybe I should actually write through all the give me a second. I'm gonna need I can't do this off the top of my head. Or maybe I can't, I don't know. Okay, right, so. So this is our cost function, right? Because this is how we define mean squared error in general. And then this is our prediction. Yeah.
Wait, is the cost function just a number?
Just cost function just outputs a number.
Oh.
Cost function tells us how bad a prediction, remember? Right? And so for a given data point xi, I can calculate like, well, how I can, this is saying make a prediction using this linear regression model, right? And then this is saying find the difference between my actual output and my predicted output, right? Yes,
Why are you putting the data right next to the X line?
because xi is my input, right? And then what am I using to make the prediction? What makes the prediction? The linear regression model, right? The linear regression model is that, right?
Oh,
Right, so I'm making a prediction with the linear regression model. That's theta xi, right? And then I am finding the difference between my prediction and my actual output, squaring it, and then finding the averages.
so data Xi basically represent each of the data points.
Yes, each of the outputs of the data points, right? Right, like the prediction of my data point.
Got it.
Okay, good. And so from there, right, like this can be expanded into this really long thing, right? And so I might write like the true cost function then, like if I were to expand it out, looks something like this. And this is also sort of why like you need to like not be phased when you look at terrible math. You just need to sort of try and understand the concept. This means make a prediction using the linear regression model. This means find the difference between my prediction and my actual output. This means square that, find the squared error. Sum it, average it, mean squared error. Make sense? Good, okay. The gradient, right? And so note that this function, I've labeled it J vector theta, right? This is a vector of parameters theta 0, theta 1, all the way to theta n. This defines how many inputs are there? Can someone answer that question? N plus 1, right? Because there's n and then plus the bias vector. Yeah, sorry, trick question, right? So this is an n plus 1 dimensional input, and then gives me one output, a value, a cost function, a cost value, right? I am trying to find the gradient of this cost of this really high dimensional surface. Does that make sense? Right? And to do that, the gradient is pretty much the gradient by definition means find me the rate of fastest ascent at a point in this multidimensional function. Does this make sense? Okay, it's great. And that is just defined as the partial derivative of the cost function with respect to each parameter. Does that make sense as well? It's a vector, right? Because, well, we want the gradient to tell us the rate of fastest ascent. Yes.
The partial derivative is the derivative of one, and then you treat all of them
As constant, yes, correct. Remember that the partial derivative, like if you took 2D, hopefully you guys did. Actually, is that a requirement? No, it is not a requirement, but good for you to take 2D if you're interested in that, right? It is if you take a surface, hold every single direction constant, hold every value constant except for one variable. Find the instantaneous slope along that point, right? And then do that for every single direction, right? And then that gives you your gradient. And so that, if like the derivative gives you the instantaneous rate of change, well, then the gradient would give you the instantaneous rate of change along each direction and thus the fastest rate of ascent. Does that make sense? Oh, great. Okay, yes.
Do you use like sum all of them up or
But somewhat up.
like the slope?
Oh, no, I literally put it, like, stack them onto a vector. So I find, so this is an n plus one dimensional function, right? N plus that one dimensional.
Like the vector represents the instantaneous rate.
Slope with respect to one direction,
And then you do that for each of the.
each of the directions.
And then you.
And then I just put it into a vector. So this is, and this is a n plus one by one dimensional vector.
Oh.
Does that make sense? Cool. And that tells me the rate of fastest ascent, the direction and magnitude of fastest ascent. Yes.
How do you find descent?
Oh,
Here.
if I know the rate of fastest ascent, well, then the rate of fastest descent is move along the opposite direction, right? Okay, very nice. So, well, then this becomes just like a really, really crappy math problem in which, like, all I have to do is find, well, partial derivative of this with respect to this, right? And you can do it and write it all out. I don't know, should I do it? Do you guys want to see this or no?
It's not really.
It's just pretty gnarly. It's kind of not worth the time. Because I'm looking at it, it's like 10 steps long and I don't want to explain every step. It's not worth it. The point is, you can get this gradient by doing math, right? And then using this, right, you can, if I give you an initial set of theta 0, theta 1, all the way to theta n, like I'm existing in this parameter space, right? I can iteratively move along this direction, this negative gradient, right? To minimize my cost. Does that make sense? Okay, yeah.
So then when you negate it, do all the entries in the vector become negative?
Oh, yes, yeah, it's minus one times. Okay, great. So that was what we talked about last time. So that's pretty important. And honestly, like I could spend the entire 45 minutes or 60 minutes that I have doing that, right? If you guys want to talk more about that. Or I think I'll probably get a little bit more into what we're talking about today. So, okay, we talked about fast gradient descent, stochastic gradient descent, mini batch gradient descent. And so we're going to continue our discussion of the linear regression model, which, and this time we'll introduce the concept of feature transforms. So, and also we'll introduce the concept of regularization, which is a set of techniques for preventing overfitting, which is a topic we discussed 2 weeks or 3 workshops ago, one of the two. Okay, so yeah, recall the standard form of the linear regression model. It's right here. Right. And recall that the linear regression model attempts to find the hyperplane that best fits the data. Right? That makes sense? Good, right? I've very crudely drawn it here, right? Yes.
Can you please explain what a hyperplane is?
A line is like, okay, you have a line in 2D. Right? If I am working in 3D, I have planes. And then it's a generalization of linear algebra. In higher
3D, so it's like a multi-dimensional line.
multi-dimensional plane.
Because you can't exactly visualize a 4-dimensional like surface, so we just say hyperplane, and it's some imaginary plane that spans, say, 4 dimensions, 5 dimensions, 6, 1,000 dimensions.
Correct.
Okay, so let's say we're in the nth dimension, basically, like some hyperplane is just the n minus 1 dimension, basically.
Yes, yes. Yeah, so if I'm existing in this 3-dimensional surface, right, then the sort of highest dimensional object I can sort of or like an object I can visualize in the space is like a 2D plane, right? If I'm in a 3D plane, I can visualize if I'm in a 3D space, I can visualize a 2D plane. Technically, I can visualize a 3D subspace as well, but it doesn't really matter. The point is, the linear regression model fits like, well, in 2 dimensions, a line through a plane, right? In 3 dimensions, right, a plane, right? sorry. In a linear regression model in 2D fits a line through a set of data points. In 3D fits a plane through a set of data points, and in 4D and above fits a hyperplane through a set of data points. Does that make sense? Cool. So, okay, so what if, like, so far we sort of assume that our data is like nice and dandy, and like things are like, let's say the data points are all like sort of plus or minus around this plane, right? And we can fit this hyperplane very well, right? But what if the sort of true relationship between the input features and the output and the output is nonlinear? So like the simplest example I could come up with is like this, right? Like if my data set looks like a quadratic, like if my data set follows a quadratic model, right? And I attempt to fit like, and I'm like, I have to use a linear regression model. I have to, right? For some reason, right? Well, then I'm kind of cooked, right? Like, regardless of how I try to optimize my parameter, so like, remember for a straight line, it's like y equals mx plus b, or y equals theta 0 plus theta 1 x1, and therefore my parameter space, or my set of parameters is theta 0 and theta 1, and therefore my parameter space is spec is the set of vector, or is the plane defined by theta 0 and theta 1, right? I'm trying to find the optimal theta 0 and theta 1 that gets me the line that minimizes this MSE function, right? That's what we've been talking about, like, well, what I've just been talking about for the past 20 minutes, and what I've been talking about for the past like 4 weeks, right? But this line, no matter what I do to it, is gonna be crap, right? Why?
It's the wrong dimension.
And it doesn't fit well. It's just a constant while the data is like a quadratic.
Yes, like the underlying assumption of this data set is that it's quadratic, yet I'm trying to use a linear model to try and fit it, right? I have a, like my model, my predictive model has a strong set of inductive biases, if you recall what we're talking about. Like the set of assumptions that it uses is strong. It's too strong, in fact. It's strong in the sense that I'm constraining the relationship between my input variable and my output variable to be linear, right? But I don't want, but I need it to be like looser, right? Higher dimensional, right? So, can we somehow modify, like, let's say for some reason I really wanted to stick to this linear regression model, right? Like, I'll sort of motivate it a little better later, but like, let's say I had to do that, right? Why might I, like, what are some techniques I can do to like make sure I actually fit a curve? Well, as like the sort of lecture like name suggests, it's feature transform, right? So a feature transform is literally just a function. It's a function phi that maps from like RD to RK. By RD, I mean it maps from like a d-dimensional space where my vectors are like d dimensions, and maps to a k-dimensional space, and we don't have any restriction on what like k has to be, right? It could be as long as it's any positive dimension, right? And it transforms input features. And so why we care about feature transforms is it makes data more suitable for modeling, right? So how will it make this data more suitable for modeling to make my predictions look better? Okay, well, okay, so let's consider this like training data set again, right? I have a bunch of xi, yi, where the true relationship between x and y is this quadratic relationship, right? And it's representable by some sort of secondary polynomial, y equals ax squared plus bx plus c, right? You probably dealt with this before. And so we fit a standard linear regression model. So as I said, we're trying to, like, we're fitting this theta 0 plus theta 1 x1, right? Through this, like, with this data set, we're trying to find the optimal theta 0 and theta 1 that minimizes my MSE, right? And we might do so either by gradient descent, as we've talked about before, or we might do so by a direct solution of the gradient, setting the gradient equals 0 and then solving, right? So those are, does that make sense? Right, so that's our problem setup, right? And so, well, regardless of whatever theta 0, like regardless of whatever theta 0, theta 1 gradient descent or direct solving of my gradient equals 0 came up with, the learner is going to be crap. Yes.
Please quickly go over the problem setup for PHIT.
So, okay, yeah, I'm going over through it right now, right? So, as I said, we have a quadratic data set, right? And I have, like, in this case, I have a quadratic data set and I'm trying to fit a line through it, right? No matter what I do, my fitted lines can be tracked. Very understandably so, because my relationship is quadratic, yet I'm trying to use a linear model to try and fit through, right? It would never be good. What?
I don't think that's me.
Right, it would work, right? Okay, great, correct, yes, it would work. So the point is, I want to somehow transform like my data set to make the data, or I want to still be able to use my linear regression model. But how can I sort of transform my data to allow me to continue to use my linear regression model? What I'll do is use a feature transform. So I've defined a feature transform as a function that maps from some d-dimensional data to some k-dimensional data. Okay, yes.
Would D be 2 and then K be 3?
D would be 2 in this case, yes, but here I like we're doing a little trick here where we're augmenting it with a 1. So actually, yes, it is 2, right? Really, our data set, like as I said, our data set is xi's and r, y's and r. So really, it's actually 1, right? So D is 1, right? Because look at my input, right? Like I have one axis in my input, right? So I'm mapping from this one-dimensional data, right? And in this case, like, so I was gonna get there, but k is 3. So what we can do is we'll define a function phi mapping from r to r3, such that phi of x equals 1x and x squared. What the heck does that mean? That means if I give you a point along this x-axis, right? Let's say that this x is like 9, right? Well, I don't know why I picked that number. 10, right? Then when I plug in phi of 10, I get 1, 10, 100. Make sense? Cool. I do that to every data point in my data set. Every xy data point in my data set. I apply this feature transform to every data point in my data set. And what that ends up, or what that results in, is a new transformed data set that looks like 1 xi, x squared, and yi, right? Does that make sense? Is anybody confused? Does anybody have no idea what I'm doing? Yes.
So we're using phi to take in the one-dimensional input of our linear transformation, because we want to use our line in this case. And we're using phi to take that one-dimensional input and transform it into three-dimensional. That way, it more accurately models what our actual data set looks like.
The that way part we'll get to, right? What it's actually doing, I'll show a visualization of in like literally a few, like 2 minutes. What we're doing is, like, I began this data set I could have thought of as an XY data set, right? Like a bunch of x's, like -1, 3, minus or 0, 2, 1, 1, or something, and then it's just a bunch of that. What I'm doing now is converting it into a data set that looks like I'm effectively artificially inducing a greater feature space. I am increasing the dimensions of my inputs, right? Artificially. by looking at X, like I'm adding extra columns to my data set effectively, right? How did I map from here to here? I used my feature transform. For each XY pair, I plug it through this, right? So -1, 3, I just look at, oh, I only need to plug in the -1, right? Or I only look at really, sorry, to be more precise. I only really look at here, -1, plug it in, it becomes 1 -1 1, right? Right, and then I produce a higher dimension data set, yes.
So I understand the feature transform takes like one vector, turns it into another.
Yeah.
But where did the y I have been?
Yi is my label, my corresponding output.
Oh, for that.
For that vector, right? It's like,
For the transform vector.
it's the same thing.
Oh.
I haven't changed my input.
Oh.
Right, so I am like, for this -1 example, right? My yi is still 3, right? So that's what I'm doing, right? And why we do that is because when we add dimensionality, what we can do is or actually wait, let me think about this a little better. Oh, right, yeah, sorry. What we can do then is now treat this as like a separate data set, right? This is like this is now D-transform, right? I've called this D-transform. I can train a linear regression model on this D-transform, right? But what does this linear regression model look like? It would just be, I have three inputs, right? So that'd be, but one of them's always 1, right? So I would have my linear regression model would look like this, right? And if I expand it out, it looks like this, which fits the form of our y equals ax squared plus bx plus c. So I'm not sure if that made any sense. I did not really, okay, 5, okay, great. Good questions. Let's start with, yes.
If we're solving a quadratic, which is a two-dimensional thing, and we have a line which is 1 dimension, why did we go up to 3 dimensions?
So what we're doing is, I will try and draw this well, because it's kind of hard to draw, but imagine for each one of these x, so with this, I clearly can't fit a line, right? That's kind of obvious. Now, imagine what I did was extend the third axis. And now, this is my x squared axis, okay? For each data point, so let's say this is like 1, right? Well then, I will map this point now onto the same y level, but I'll push it towards the x squared. So if this was 1, then I'd map to its new, if this coordinate was like 1, 0, its new coordinate would be 1, 1, 0, right? And then if this was like 2, 4, its new coordinate would be 2, 4, 4. Okay, and if I had 3, if I had like 3, 9, I'd have 3, 9, 9. Okay, something like that. When I push it out, right, you can imagine that this parabolic curve now becomes almost a plane in this higher dimensional space. Does that make sense now? I'm seeing slow nods and that's good. That was better than before. Okay, because that's a very crucial part. Yes.
So is it kind of like how if you have data that like would fit a two-dimensional function, like a quadratic, trying to fit a line to that has a lot of air, but trying to fit a function that has like x to the 3 to something that should have say x to the 5 is like easier, or like as you get higher in false dimensions, the actual difference becomes smaller, or is it, am I missing?
So. We are pushing the data. Okay, so, okay, let me try and process that question a little bit. We have a model, right? This linear model, it's a linear regression model. It will not fit our data set no matter what we do, right? Like, no matter how hard I try to optimize data 0 and data 1 using my MSE, gradient descent, solving directly for gradient, it will be crap. Why? Because the inherent assumptions built into the predictive modeling itself via, like, well, the fact that it's a line, effectively, aka, it's a line. It's like, you can't make a curve out of a line, right? So, because of that, we're like, shoot, like, what can I do? Well, note that I said it's a line, right? Like, my predictive model is a line. But remember, I said it really is like the linear regression model finds the hyperplane that fits the data point the best. So it's not just fitting a line. So if I can it's not just really fitting a line, it's fitting it is fitting a hyperplane to the data points, right? In this case, the hyperplane is just a line, right? But if I can somehow extend the dimensionality of like if I can move this dimension, if I can move these data points into a higher dimensional space in which the data points look like a hyperplane, then I can still use my linear regression models. Does that make sense now? Right? The assumption of the linear regression model is that I'm fitting up, like, is that, like, I'm fitting hyperplanes, right? In this case, in this one-dimensional case, well, a hyperplane is a line, so I'm fitting a line through this data point, through these data points, right? Can't fit line through data points, it looks like a curve. If I make data points look like flat plane, I'm okay, because my linear regression model allows me to model flat planes. Make sense?
So you're essentially fitting the data through a hyperplane instead of fitting the hyperplane through the data?
Well, you're still fitting a hyperplane through data. You're just moving the data. You're just moving the data to a higher dimensional space in which it can be it can be modeled by hyperplane.
Okay.
So yeah, there's a bit of nuance there because because the data is never doing anything.
Yeah, you're not changing.
Right. You're not. Yeah, you're not. Yeah, you're not fitting, like, you don't fit a data to a model. You fit your model to data. So right.
I mean purely in terms of just how it's representation, how it's represented, not like you're actually changing your data. Like you're making in this case, you're changing the way your data is represented. In order to fit the hyperplane, the linear regression found that's a vessel.
You are manipulating your data into a higher dimensional form via this function that you defined in order to, yes, have this linear regression model be able to fit nicely onto this data.
Okay, makes sense.
Right? And so, okay, Shreya, could you
You have to use your computer to email it to me because the airdrop failed.
Oh no!
Yeah.
Okay, let's see. Actually, let's see if I can just directly connect to it. Is there a way? Because there's a very nice visualization of this that sort of very graphically explains what is going on. Down. Is this how you connect it? Damn it. Will it automatically? Just making sure. Oh, do not see my text messages. Oh, what CD desktop /10. Find my notes. Okay, you see this? Oh, beautiful, isn't it? So in my original space, right? Let's just make sure I'm not showing anything I should be showing. Perfect. Yeah. No. Nothing weird. Just like I've got private information and like passwords and all that.
API keys.
Perchance. Yeah, I'm not gonna say which ones. Okay. Yeah, I have an XY data set, right? You can imagine as a setup was, I fit a line, right? That line would be trash, right? So what I do instead is I project into this higher dimensional space my data points. Sorry. So if you look at this, right, the data points are the exact same. I actually flipped it around, but yes, you can see that they're the same data points, right? I've just projected it into this higher dimensional space, right? But when I reproject it back onto my original onto my original feature space, it looks like crowd, right? But note, in this higher dimensional space, wow, this is really finicky. Doesn't this look like a hyperplane? Right? Does that make sense? So effectively, what I've done is I had some data points, XY data points, that had some quadratic, that in a second. I had some XY data points that represented a quadratic curve, right? I could not use a linear regression model directly because a linear regression model would be y equals theta 0 plus theta 1 x1, which is a line, and a line in this two-dimensional space, well, looks like a line and cannot fit a curve. What I can do is recall that, linear regression models fit like hyperplanes through data points, right? So I can somehow turn my data points to look more hyperplanar, and how I do that is by applying a feature transform, right? Well, then I can use my linear regression model. And so in this case, I note that, oh shoot, like this kind of looks like quadratic, right? A quadratic curve. Quadratic curve goes up to x squared, right? And so what I want to do is define a feature transformation that maps all my points, like all my xy points, to 1x x squared. So then when I do my linear regression, I get like this, which simplifies to a quadratic model. Does that make sense? Yes. That's the big whoop of today, like the most important part of today. So we sort of demonstrated that we can apply linear regression models to represent nonlinear relationships. That sounds very unintuitive, but we do so by a feature transform. Does that make sense now? Okay, yeah.
What does D and what does K mean?
D is just any dimension, input dimension, K is any output dimension. This is like just sort of math formalities you will see whenever you deal with.
But is there like a formula for like computing?
No, feature transforms are whatever input. A feature transform is just a function, right? It's just a function that maps from an input dimension to an output dimension, right? Did I say any sort of specific dimensionality there? No, right? So, well, how do I represent it? I don't care. I just say D and K, as long as D is a positive integer and K is a positive integer. That's sort of implied.
Does K have to be greater than?
No, it does not. Good point. That's it. That's a good point. No, it does not. In fact, like when you reduce it, that's called dimensionality reduction, right? Like that, or feature selection. You are specifically choosing, like, there's a mapping function. Like this. Also, this is very important. This is like supreme. Actually, I just remembered. This is supremely important because this relates to neural networks. If you've studied neural networks before already, then you will know that, or maybe you haven't seen this sort of relationship before, you'll know, oh, there's layers and stuff like that. Each layer is a feature transform. Each layer is performing a feature transform. It is effectively turning your input data into some sort of higher or lower dimensional representation, right? Modifying it, performing performing a sequence of feature transforms, and then applying a final linear regression model or the linear classifier models, which we'll go over again, right? To make a prediction. This is sort of why I've been guiding the lectures the way they have been, right? I gotta first teach you like what a linear regression model is. I gotta teach you how to optimize. I gotta teach you, well, what feature transforms are, and then how to make predictions for classification models. And then boom, now a neural network is just a sequence of feature transforms followed by a linear regression model or a linear classification model. So if you've understood, like, if you've already studied neural networks before, this should be sort of like oh, there are like reasons for why we're doing what we're doing moment, right? This is why, like, we are converting our data into representations that are supposed to be more easily linearly separable if you've done classification, or easily modelable by feature transformations. Yes.
Is there I guess it's kind of a similar question too. Is there some function for it? But is there generally a way you should go about finding what the transform phi should be?
Great question. Fantastic, fantastic question. Domain knowledge. And this is also actually, that was gonna be the start of my neural network presentation. Like why this method sucks. Because half the time you don't have domain knowledge, and half the time if you're like this toy example that I projected onto the screen, well, you could immediately tell, oh, it's like quadratic. But like if you have already a really high dimensional data set, you're not gonna be able to do that, right? You can't figure out the feature transform. And a linear regression model is not gonna work. And so you're cooked, right? And so we want a way to automate this sort of feature transformation finding process. Neural networks effectively do that. Well, neural networks, you still sort of have to like assume if you know how neural networks work, like there are an amount of neurons that defines your feature like that defines the output dimension of your feature transformation. Right? So you're still making some sort of assumption, but you don't actually have to manually define one, which would be even worse. You can imagine. Right? Yes, first.
So are you saying that feature transform is really bad? Are you saying that feature
Manual feature transforms are like nobody really does them. But I am teaching you this because you need to.
So that's manual feature transform?
Yeah, I manually defined this function, right? This function that maps from x to 1x squared, right?
And why are you saying it's adopted?
Imagine I have this really big data set, right? Millions of data points, tens of dimensions, or dozens of dimensions.
So you're saying it would be bad from like a time complexity standpoint?
It would be a bad from how would you do it standpoint. Like how would you even go about defining a function? Like if I have 10 dimensions as my input, right? I'm trying to predict house prices using 10 input variables, right? And I want to say fit a plane for it, right? Or find it or use my linear regression model somehow to be able to model relationship.
So are you saying that?
How would you do it?
Alright, so you're saying it's harder to do it with more data?
It's harder to do it with like higher dimension, more data points. You can't visualize it. Well, how are you supposed to come up with this sort of function manually? You can't, right? Unless you have some sort of, unless you're like a genius in some sort of like housing market prices or whatever, right? But if you were, you wouldn't be doing this. You'd just be, well, buying and selling houses, right? Okay. Yes.
So it's more so the idea about feature transforms that are important rather than like,
Oh yeah.
that's really
Oh yeah.
physical.
You're like, you will do this for an assignment in 178, and then you will never touch it again, but you know how to do it now. Great, right? Actually, you might use it sometimes, but okay. I guess we're not going to go into regularization. I guess we'll just do that next time. That's fine. This is important. Let's see. Oh yeah. Note that like whenever we do like just even augmenting variables, we're effectively also doing a feature transformation, right? I'm mapping from my if I'm performing linear regression over like these XY data points, right? Well, if I want to represent it using linear, or my linear regression model would look like this, right? Which is just this, right? But I am augmenting each of my x1 data points to become a vector 1 x1, so 1 xi, right? So whenever I am forming linear regression, I'm effectively doing like a feature transformation, but a very toy one in which I'm mapping from R to like R squared such that b of x is 1x, right? But that's just notation, just to let you know that we've already been doing feature transformations effectively, implicitly. Okay, yeah, and why would we? Well, okay, yeah, like why might we also actually use it? Well, most people actually don't, but like sometimes, okay, yeah, linear regression's fast, right? So if you want to just do something fast, right, like you just need a quick way to model a relationship quickly, you might do this, right? That's a good way of doing it. And again, like with MSE and linear regression, you can directly solve for the gradient equals 0 right? And you will get the optimal parameters that give you the hyperplane that fits best through the data, right? Like that fast. So that's it is fast. That's one way you do it, but there are issues, right? Yeah. And sometimes finding the exact dimensions that like allow you to fit it, like, or how do you say it? Finding the exact dimensions that allow you to fit a plane through it is difficult. And also, even if you get it, like you might have to increase the dimensionality of your data to be really, really, really high, in which you introduce other problems like overfitting. Because your parameters or how do you say it? You have so many parameters that it will attempt to try and fit the data points perfectly in your in your training data set, such that when you actually test it on a testing data set, it will perform like crap. Right? Okay. Let's see. Okay, yeah, that's pretty much like the big whoop, the big talking point. Does that sort of make sense to everybody? Good. Anybody have any lingering questions before we like move on to the coding segment? Yes.
For like the grading portion, like the MSE, do you still do you grade all like the differences equally, including like the feature transform ones? Because like if one of the parameters is like just a feature transform, wouldn't it not matter like as much how close it is to the projected self?
Sorry, I'm a little confused as to what you're saying. Would you mind repeating the question?
I'm saying like if like for instance for that is it only graded
For
is the
what?
final grading only how close it is to X and Y or the original data points, or does it grade how close it is to everything including the feature transform?
So, sorry. I'm still a little confused as to what you're asking, but I think I have an idea of what you're asking. Your MSE will not change. Like if on this original data set, before I introduce this x squared dimension, right? I have this xy, right? And I have quadratic data points and I try to fit a line, I could calculate MSE, right? When I introduced this extra dimension, shoved all the data points accordingly, right? And fit a hyperplane, right? I can also still calculate an MSE, right? I'm still looking at the difference between my actual values and my predicted values on the hyperplane, and then squaring it and then finding the average. Does that make sense? We good? Or okay.
Gears are turning.
Yeah, okay, yeah. If you have any more questions, you can ask me like outside. Yeah. Any other questions from anyone? No? Great, thank you. So yeah. And lovely Shreya.
Thank you.
Now I have 117 homework to deal with before I get booked. No, computer vision. Oh, it's being out here. It's yeah.
Is that the project course?
Quick project course. It's really fun. It's difficult. You need to keep asking questions to the professor if it's yeah. Tips if you have Professor Byrne, he's such a nice professor. Keep asking questions. Yeah, he'll always answer. Just side. Yeah. Thank you, everybody.
Okay, guys, so today what we're gonna be going over are primarily linear regression and cross-validation. So basically, this is going to be looking at, start off with some XY data set. And it turns out that your data set is not perfectly linear, as you saw in the past. we have some curves in this data set and we need to account for that with our model. So in our previous coding example, we modeled a perfectly linear data with using y equals mx plus b, as seen over here, where we have two parameters, theta 0 and theta 1. But now, well, as Aston was talking about, we can model more complex models by taking our parameters and changing the dimensions that they're in and using a feature transform phi. By doing this transform, we are still linear in parameter. If you guys remember previously, we talked about the concept of parameter space. As we employ a feature transform on our data, we are still linear in our features because our parameter space is now multidimensional. So here's what we're going to take a look at. This is our data here. This is the first 50 elements. Here's our x value, here's our y value. Ignore y true here. Y true is basically the actual value. Say that we already knew what the correct model for this data was, what the value of y would be for that correct model. So in real life, you would just have these columns here, x and y.
Sorry, do we have the link to this or no?
Oh yeah, I forgot to put it in the chat.
Chatting.
1 second. Here's workshop. Ah. There, let's go look at that. This is the exact notebook that I'm following through right now. I did not. If you guys want to open up the other version of it, which is like the fill in the blank version. Fill in the blank. It's here, just open it up in Colab like I do here. So first, let's just take a look at our data. Here's what our data looks like. Ignore the green line for now, the blue dots here. We can tell that this data here is not purely linear in fashion. It has curves to it. And so to account for this, we can take our normal data here, which is like 0, -1 up to 3, 0.8, and employ a feature transform on there. So we're gonna make two models and compare them to each other. One's just gonna be a normal linear regression model, y equals mx plus b. We're just gonna do that. The second we're gonna make is that same exact model using the same linear regression class from scikit-learn, but we're gonna apply feature transform before that and add more data to it. We're going to use degree 5 for this polynomial feature, as we can see over here. So previously our y value is, or x value is 5.05. And so we're going to take this and we're going to make it to the power of 1, square it, put it to the third, the fourth, and the fifth. So this is our quote unquote new data, and this is what it looks like when you employ feature transform phi on like one example row. So if you look at that, here's our data, here's the actual fit of what we want our data to look like. This is just a linear y equals mx plus b. Yes.
What's underfitting?
Underfitting is when your data isn't when your model is not capturing your data that well in the training, which means that it's not like, if you look at the training error, it's not doing that well because it's not truly understanding the full extent to which what your data is showing. Versus overfitting is your data is looking at too much, your model's looking too much into the data. It's listening a lot to the different parts of like the noise, stuff that it's like too overtuned to your training data set. So underfitting is you're not looking at your data set enough, overfitting is looking at it too much. The way you can think about it is like listening to music and you're turning the volume knob. Underfitting would be like your volume is way too low, you can kind of hear it, you can kind of make out what the words of the song are, but not that much. Overfitting would be you can hear it way too well and you need to turn it down a little bit. Yes.
So then how do you solve the underfitting over?
We will talk about that soon. So one of the ways is by employing a feature transform like this. We can see here, we are severely underfitting our data. There's parts to our data that we are not looking at because we don't have enough parameters in our model. Versus here, once we employ that fit, remember we had 5, 25, 120, etc. We were squaring that x value so that we can make up for the fact that so we can make a linear model with more parameters and fit this model. that for me much better, we have R squared value of 0.93 here. Yes,
So when you have an overfitting problem, is it called feature reduction?
if you have an overfitting problem, there's a number of ways you can deal with that. One of them is feature reduction, which means that like you have way too many polynomials. Instead of 5, I said I'm gonna do 15 and see what happens. We can like just do that right now just to see what would happen. Let's say we make this 5 up here 15. Look at our models.
Okay.
Wait,
Look what happened to it. This is the
Right.
degree 15. This is overfitting.
It looks perfect.
It's
So beautiful.
looking at the noise of the data. This is not a real data. That's our true fit. It's looking at the noise here and it's overfitting our data too much.
it
Yes.
looks like it got smushed.
Yeah, exactly.
It
It's
memorized
looking-
the data too much.
Exactly. It's memorizing. It's like the way I think about it is like, let's say you have a midterm coming up and your friend gave you what you think is the actual midterm paper that's coming up next week. And you're like, I'm not gonna study anything. I'm just gonna look at the answer key to this midterm, but I'm gonna be fine. But your professor actually took and made his own exam, and now you don't know anything besides what's on that previous midterm. So you'll know some stuff because he kept some of the questions, but the ones that he changed, you're not gonna know anything because you didn't actually study with the material. You just know what you thought was the actual exam. You know? Let me fix this back to 5 again. So that's an example of overfitting, and we're gonna look at that later on. The main idea here is that linear regression can model nonlinear relationships by transforming the features with phi. Yes.
So when you have an underfitting problem, what is it called? Is it, I mean, for overfitting, it's feature reduction. What's it called for underfitting?
Usually it's like adding more features to it. I feel like the problem you'll have more than underfitting is overfitting, and overfitting has a bunch of solutions to it. Feature reduction is one of them. Another one we'll learn about is regularization, which is like sort of forcing your features to be smaller, even though you have a large degree. We will talk about that at the end of this notebook.
So regularization solves the overfitting problem?
Yeah, it's another way to mitigate that problem, but we will talk more about that very soon. So we're gonna look at this idea in another way using a hyperplane. So in a new feature space where we have x and x squared, that means we're in a new two-dimensional hyperspace. We now have two parts to our data, x and x squared. Versus before we just had x and y. So now if you want to, when you just have x and y and you make a graph of that, it's just a normal 2D plot, right? Versus if I feature transform it, now have x squared and y, this is now a 3D plot. So we're going to look at that. So in our original feature space, it's just one dimensional, we just have x. We transform it, it's 2D now because of x and x squared. And so remember before we were talking about degree 5, we're going to go to degree 2 because that's easier to visualize, you know. Let's look at that in both spaces. You see that? This is the same exact data set, but now so looking at from x to the 5th, looking at x squared. This is what x squared looks like. It's not fitting it that well, but it's slightly better than just linear. 1 second. In a hyperplane, we can plot the same curve, and it doesn't look as bad as it did before. And this is the same thing for the original data and the same curve on it, just projected on. What I'm trying to highlight here is that something that is non-linear in 1D may be linear in another dimensional space. That's the main idea. Just because it's non-linear in 1D does not mean that it's non-linear for every dimension. There can be a dimension that will make this this data set linear. Does that make sense to everyone? Okay. So when we transform the space, we fit a linear hyperplane. And we project this back on, it becomes a curve. And this is how linear regression models model nonlinear relationships. Now, the next thing we're going to talk about is this idea of k-fold cross-validation. So remember earlier, we talked about we can do feature transform. We can do x squared, x cubed, x to the 5th. We did x to the 15th earlier. You have so many choices of degrees. How do we know which one's the best? How do we know that x5th is the best? What if x to the 6th is the best model? How do we know which one's the best? Do you guys have ideas for this? How can we select the best model? Yeah.
Try them all.
Yeah, that's one. You could try all of them and see which one gives the lowest error, which one is performing the best on our data. That's one of the ways we can do it. But how would we estimate that data-wise? Because let's say I have 100 data points. and I really want to see which one's the best. If I train on all 100 data points and then I test on them, my model's gonna do pretty good. What are some other ways? If I have 100 points and I wanna know which model is the best, what are some ways I can deal with that? Any ideas?
I have one question
Yeah.
about to try them all. Isn't that gonna take forever?
It can take forever, it can take a really long time. That's why,
It's
like,
not scalable.
it's not, let's say that like the best dimension for your data is 100 x to the power of 100. If you're gonna try 1 to 100, that's gonna take a real long time. That's why if you guys remember Aston saying some domain knowledge is useful when you're doing feature transforms. You need to know something about your data before you employ a feature transform to avoid wasting time and trying every single model. But it's like a good solution if you have no clue what your data is about.
So is there a more efficient way of doing this?
You just have to know what your data has in it. You gotta have that's why visualizing your data is good. If you plot your data onto just a 1D X and Y, you can have some idea on how you should go about doing a feature transform. Let's go back to the cross-validation, the idea of testing your model. It's like, let's say that you have a midterm next week. And you have the following, you have a bunch of homework problems and you have one sample midterm that your professor gave you. And you wanna know you wanna do good on your midterm, how are you gonna study? What are you gonna do?
Do all the homework problems and the sample midterm?
Yeah, you can do all the homework problems and then you can test yourself on the sample midterm, right? What if you instead do all this homework and you look at the answer key of the midterm and then you do the sample midterm? Would that help you? That would not help you, right? If you just looked at all of the homework and you looked at the answer key of the midterm and then you took the sample midterm, that's not gonna help you. You're already not gonna know the answers. That's a similar idea when it comes to testing your models. Just like you do with studying for your midterms, you can look at the answer key and look at the homework problems and do those at the same time. So you can understand what's going on. And then you can test yourself on the sample midterm and then, correct your mistakes, how that goes. And then your midterm that your professor gives you, that's like your final test because you cannot look at the answer key for that beforehand. Similarly, what the idea is with cross-validation for the model is that if I have 100 data points and I have the answer to those 100 data points, I'm going to take that and split it into parts. One of the common ways is you split it into, let's say, k equals 5 equal parts. You train on 4 of those parts and then you test yourself on the last one. It's like, let's say you didn't have a sample midterm, all you had were homework problems. You take all of your homework problems, you split them into 5 parts, you study and do four of those parts, and you test yourself on the last part. That way you can test yourself on how much you know the knowledge. Same thing for a model. You can train it on, let's say you have 100, what's 100 divided by 5? 20. You train on 80 points, and then you test yourself on 20. Then you do that again, you split into another 5 parts, train on another 80, test on the other 20. Yes.
Is this the whole 80-20 test?
This is one of the ideas behind 80-20 split. That one is you do one split, 80-20, and that's it. This is you do an 80-20 split 5 times.
Does it still linear time?
No, it's not linear because you're doing it 5 times, but it's better because let's say you have the 20 points that you got they're just terrible, they're outliers. It's like you split your homework into those parts and the 20 questions that you're testing yourself on are the worst and hardest questions that aren't representative of how the midterm is gonna be.
What if the test data are just outliers?
Exactly, that's what you do it 5 times. That decreases the chance of your test data being bad.
Oh, so that's why you do it.
That's what you do multiple times. This gives us a good estimate on how well each model will generalize to new data because you're doing it multiple times. So now we're gonna do this, and we're going to use these degrees to test our model on.
Do the degrees mean anything?
Yeah, this is just like x to the first, second, third, just chose them randomly. We're trying to choose some like smaller values and then some bigger values. Now let's look at what we got here. So you can see here that cross-validation MSE is the average of how well we do on that one remaining test set. Remember we split it into 5 parts, 4 of them are training, 1 of them is testing. This is the average of those 5 testing sets we have remaining.
Oh, is that on the left?
That's what's here. So these are the degrees. We can see that you want MSE to be low. You guys remember mean squared error?
Basically, just a cost function.
It's basically just a loss function. your prediction minus the actual answer squared. Subtract them, you square them. And then you take that value and you add it across all of your data and you divide it by the total amount.
Oh, so we want low error.
You want a low value here. And you can see here that for just y equals mx versus y equals x, not even any m, it's really high. And then as we add degrees, it gets low because it's the smallest value, and then it goes back up again. Why does it go back up again?
Because you're overfitting.
Because you're overfitting. That's how it's going up again. And you can see here, our best fit is x to the power of 10. One of the bad fits is x to the 15th, and x to the first y equals mx plus b. That's also underfitting it because you're not looking at the data enough. Does this make sense to everyone? The idea of cross-validation and overfitting, underfitting? Yes? This is one of the best ways of seeing how well your model does. Cross-validation is an excellent way of doing this because this way you're removing the issues of outliers, and it is one of the best ways of testing your model, especially if you have like a decently sized data set, but you don't have a bunch of test data. Yes.
It's cross validation where you're just applying three techniques, like underfitting, good fit, overfitting.
It's a way of figuring out what's the best fit. So you have a range of models, do cross-validation on all of them during your training process. We make like a graph like this, and you can figure out which one does the best, which one's doing the worst. The one that does the worst is likely underfitting. And the one that does like worst in the middle-ish area, that's probably overfitting. And the one that does the best is the good fit.
So each of the 7 data points, is that like the model's performance on each of like the degree?
Yes, this is the mean squared error, cross-validation mean squared error on each of the degrees.
Oh.
That's all that is. It's just how well is it doing it on each of these. So when the degree is too low, we're underfitting. The model is too simple. It's not actually understanding the data. X to the 10th is a good fit for it. And x to the 15th is overfitting it. The model is fitting into the noise in the training data. Does this make sense to everyone? Cross-validation? Yes?
Yeah.
Yeah? Okay. I want to highlight again that when you do when you're employing polynomial linear regression, so feature transforms in scikit-learn, you use this thing called a pipeline. So this is what you would do if you had some sort of like numbery data. This is what you would do. You first want to employ your polynomial feature transform, which means you take your data in and you convert it to however many features you want. In this case, we're doing it multiple times for however many degrees you have. Let's say your degree is 5, you just put that right there. And then you employ linear regression, which is the just normal standard linear regression. I think the default just uses mean squared error. You can also further modify that to use a specific loss function if you want. But this is how you would do it. And then you spit the data to your x and y value. And then you can predict it on whatever your remaining amount is. That's how scikit-learn does it. So next up, Aston did not talk about this yet, but I'll like, go over it a little bit. You guys can ask me questions if it's because it's a little bit more complicated. Remember how we asked about overfitting and how sometimes your model is just too complex, there's too much going on, how do you fix this? And I mentioned something called regularization. Regularization is the idea of putting a penalty for making your data values way too big. You will get ridiculous values of data, for example, for the x to 15th value right here. Let's see if we can literally just print out what this is. Oh, I've got to print it. Supposed to have it.
You the controllers.
Oh, where is it at? Yeah, I forgot how to look at the specific features. I don't think it's get grams. Not degree. Whatever, it's fine, but Just give me 1 second. I know it's somewhere in here. I did it earlier. I just forgot. It's, oh, there it is. LR intercept and co-op. Co-op, that's what we want. This will be interesting. You guys will see how like silly the numbers can get at times. So I'm gonna go to, it's the predicted version. Never mind, guys, it hates me right now, so I'm just gonna ignore that. Anyway, just shows me on this, the values of your data get really crazy. So one of the ways to fix that is using regularization, where you introduce a parameter alpha that goes ahead and ensures that your data value stays small. So basically the main idea of this is thinking about it as like, you add together all the values of your, whatever your parameters are, and you add some sort of penalty to it, or you multiply it by some sort of alpha penalty value. So let's say that value is like, I don't know, like 10. It's gonna be very strict. You add that to your loss function. So think about it. You want your loss to be, I'll answer your question a bit. You want your loss function to be small. And if your parameters are really big and you multiply that by some value and add it to your loss function, then having a big value for your parameters will make your loss function big. So it's like you're adding an extra intercept to it. That is your parameters added together. And so if your parameters suck and they're really big, your loss function is going to be big, even if those values of the parameters make your loss function small normally. Yes.
Is alpha some sort of significance level?
Yeah, it's sort of like a significance level. Does that make sense to you what I'm trying to say? You have, like, let's say your parameters are, 1 second, it'll be like, I don't know, 10, 20, and 30. If we add those together, you get 60. And let's say normally with the parameter addition of 60, your loss is like 0.01. But if you add that sort of alpha value to it times 10 and you make that 600, your loss is not going to be 0.01 anymore. It's going to be some ridiculous value that's going to make your objective function be like, okay, wait, this is bad. This is making our loss increase instead of decrease when you're tweaking the parameters that way. Even though we're going in the direction of the gradient, we're getting way too specific on the training data, which is bad for us when we do testing later on. Does that make sense to everyone? Yeah.
So the lower the alpha, the more you're like, this model will be damn near perfect.
It's less regularization. You're allowing your parameters to be more ridiculous. The stricter you are, the larger you make your alpha, you're forcing it to be a simpler model. You're forcing your parameter values to be smaller. And we'll see that here. So we're increasing the strength of the regularization, and our MSE does increase. But as we do that, there's like a sweet point over here where our MSE is small. What are we doing for degree? Yeah. As we increase our values of alpha, our MSE does decrease up to a point and then starts increasing again, because having a simpler model does not necessarily mean that you're having a better model. And we saw that with the underfitting issue. Yeah.
Isn't the mean square error like increasing if you increase the significance level?
Yeah, it does, because we're forcing our model to be simpler, but there will be a point where it decreases, it hits a minimum, then it goes back up because you're forcing it to get smaller and smaller. So there again,
Is it like sinusoid?
no, it just goes down and is gonna go back up. Similar to how we saw with the degree, because here degree doesn't just keep decreasing all the way down, right? It's gonna hit a point and then start increasing again. Same thing with the regularization. It's gonna go down and then it's gonna start increasing again. Because simpler model does not always mean good. Because remember this, look at this. Degree 1 is absolutely horrid. It's so bad, but that's a simpler model technically. It's the same thing in regularization. as you increase the value of alpha and get stricter and stricter on the parameters, there'll be a point at which it's good, it does well. But then if you go too much on that too, that also is gonna harm your model, and you're going to get a model that's not even making use of your loss function, because your alpha parameter is it's not balanced anymore. It's putting way too much weight on the loss function. You guys have questions on regularization? No questions on regularization? So it just prevents overfitting by penalizing complex models. This is useful when you have something with a very high degree that is fitting slightly well, but you wanna prevent it from getting too overly complex. And here's like a good way to look at that. So where are we setting the degree here? I'm gonna get 100. Just for fun. Never mind, 100 is overkill. Let's put it back to 50. There it is. It's been like 30. There, see how you guys can see that it's like that curved shape again? With degree equal to 15, that is like a pretty good model when you add regularization to it. In fact, it gets an MSE of around like, I don't know, like 0.26. And if you go up here, I think that's almost as good as our degree 10 model. Yeah, see, our degree 10 model that performed the best there, it's around like 0.23 it's around 0.26 here. And when you add regularization to degree 15, it becomes similar like that. Around 0.26. So what I'm trying to get at here is that regularization is a good way to fix the issue of overfitting for high degree models. Don't do this for like degrees like 1 or 2. This works very well for when you know a model with high degree like x to the 15th is gonna fit your data well, but it's overfitting it. Does that make sense to everyone? You guys have questions about this? Yeah.
Can you please briefly summarize regularization?
Yes, I have it right here. So regularization prevents overfitting with high degree polynomial feature transformations with linear regression. So you take your data, you've transformed it to like the power of 15, and then you make a model and it's overfitting. And because of that, your MSE is like high. When you add regularization to it, it prevents the parameters from getting too big and causing that issue of overfitting because it forces those parameters theta to be small. We use this by tuning the parameter alpha, which is the strength of the regularization. And to figure out what the best alpha is, we use cross-validation. Does that make sense to everyone? It's just that you add this other parameter alpha to it, and alpha tunes your model extra to make sure that parameters stay small. Yeah.
So basically pick a bunch of random alphas and figure out which one figure out from which one the mean square error is the lowest.
Yeah, basically, like let's say that we really want to use the degree 15 model for this, and we decide that we're gonna choose some sort of alpha. You can choose like a range of alphas, train your model for all those alphas, which are not going to be very many. You don't want to choose like 100 different regularization strings. You want to choose them to be like 5 or 6, as we did here. And you want to see how well you do, how well your model does with cross-validation, because cross-validation prevents issues of outliers being in your test set, and measure that and get the smallest value cross-validation, the regularization strength that corresponds with that small value, and use that for your model. Yeah.
So cross validation, so like if they're like outliers in one, I'll pick a 5, like the cross validation like kind of minimize the error or the skew.
Yeah, it minimizes the effect that that outlier in one of your test sets would have on everything. Because the other 4 that have like good data should balance that out. Versus if you just had an 80-20 one split, and part of your 20% was, that outlier is gonna have a bigger impact on your mean squared error. Okay, does anyone else have any other questions about this? No? Okay, that's it.